Greetings and welcome to Distiller. In the previous class, we discussed about enthalpy, where we discussed that enthalpy is basically heat content of a particular system, right? That is known as enthalpy. All right. So enthalpy, we derived that enthalpy dH is equal to dq, that is heat transferred at constant pressure. All right, it is heat transferred at constant pressure. Hence, if we keep the pressure of a system constant and we add heat to it, then all of that heat would be converted into enthalpy of the system. All right, all of the heat would be converted into enthalpy of the system. Enthalpy for an ideal gas is CP dt, where Cp is the specific heat capacity at constant pressure and dt is the temperature difference. All right. Then, on the basis of this, we also derived on the same logic, we made another equation, which is du equals to Cv dt. So these two equations are universally acceptable. All right. These two equations are universally acceptable. And also, we had our third equation, which is Cp minus Cv is equal to R. This is again an equation that is universally acceptable. All right, for an ideal gas. So these three equations are followed for all the systems in ideal gas. All right, dH is equal to Cp dt, du is equal to Cv dt, and Cp minus Cv is equal to R. All right, and they are therefore reversible processes. All right, they are therefore reversible processes. So that is about enthalpy and internal energy. All right, and enthalpy, we also discussed that mathematically it can be written as U plus PV, right? It can be written as U plus PV. All right, so that was there that we gave about enthalpy. All right, so this was the information that we provided in the previous class. All right, so today we'll start with this problem first. This problem came in GATE 2003. 1 mole of nitrogen at 8 bar and 600 Kelvin is contained in a piston cylinder arrangement. It is brought to 1 bar isothermally against a resisting pressure of 1 bar. The work done by the gas is in joules. All right, so go ahead, pause the video and try to solve this problem yourself. Hope you could solve this problem yourself. If you could not, then let's have a look. It's quite easy. Look. So there's a piston cylinder arrangement. All right, there's a piston cylinder arrangement. So they have given everything very simply. They have just given one confusing statement, a resisting pressure of 1 bar. So let me tell you, this has nothing to do with our system. This has nothing to do with our system. This is given just to make the question slightly logical. See, I'll tell you. If let's say this is the piston cylinder arrangement. If this is my piston cylinder arrangement and this is maintained at 8 bar. All right. This is maintained at a pressure of 8 bar. This is exerting a pressure of 8 bar. So in that case, there has to be some reason why this will start moving or start pushing the cylinder. All right, pushing this piston in the upward direction. And there has to be a reason why it stops at a particular pressure. So that is why they have given that there's a resisting pressure of 1 bar here. So it will keep on expanding. It will keep on expanding till the pressure here becomes 1 bar. All right. So this has been given just to make the question sound logical. All right. What they could have done is they could have not given this thing. All right. They could have not given this thing. Instead, they would have simply said that a resisting pressure of 1 bar is applied on the top of the piston. So on the basis of that, find the final state pressure. All right. So in that case, it would be equal to the resisting pressure. All right. Because the system would stop expanding only when both the pressures become equal. All right, when the system attains equilibrium, and that equilibrium would come over here when both the pressures are equal. All right. Anyways, we'll move with this problem. So it's an isothermal process. So work done for an isothermal process, mod of work done for an isothermal process is RT ln bigger volume by smaller volume, which is equal to RT ln bigger pressure by smaller pressure, right? So they have given pressure. So pressure is given to be 8 bar, bigger pressure, and smaller pressure is 1 bar. All right. And R is 8.314. Temperature they have given to be 600 Kelvin. And this is ln 8. So let's talk about the unit. So unit is joule per mole Kelvin for 8.314 and Kelvin over here. So this becomes joule per mole. This is work done by 1 mole of gas. And they have already given that it's only 1 mole of nitrogen. So this satisfies, right? So now when we have all these values, we can calculate. So the work done, the mod of work done is equal to 10373.086 joules. All right. And this work is done in expansion. So therefore, WEXP is equal to positive of mod isothermal work, which is equal to plus 10373.086. And it can be logically also explained. See over here, the piston is going to rise if it has to reduce the pressure from 8 bar to 1 bar against a pressure of 1 bar. In that case, it will have to rise in order to reduce the pressure on the system. So as it rises, it is actually pushing the piston. So it is pushing the piston, hence force is in this direction. Therefore, work is in this direction. All right. So work is being sent out. Therefore, it is going to be positive. All right. According to the sign convention. So this is true. All right. This is the work done in expansion. All right. So this is your result. So this was quite easy, right? This was not at all complicated. Now we come to first law of thermodynamics for flow processes. So when we talk about flow processes, then in that case, we consider, let's say, we'll consider a pipe. Okay, we'll consider a pipe through which fluid is flowing. All right. So if we simply consider a piston cylinder arrangement, a still system, a non-flowing system. So in that case, the system is sitting still. So the only energy transfer possible is going to be heat transferred, work done, right? And that would lead to somewhere or the other, the internal energy being stored. That's all, right? Nothing else. But when we talk about a flowing system, something that flows, suppose in a pipe, a fluid is flowing. All right. So in that case, the fluid is going to have velocity. All right. Fluid is going to have velocity. Okay. Because of this velocity, it is going to have some kinetic energy. Right. Because of that, it is going to have some kinetic energy. It is possible that as the fluid flows, it might rise to a certain height or might fall by a certain height and then come here. So in that case, it has a height. It has a height, and height gives it a potential energy. All right. Height gives it a potential energy. Right. So apart from simply considering internal energy, work done, heat transfer, we also consider these two important energies, kinetic energy and potential energy. All right. And also we deal with one more quantity, which is work of the system. I'll explain what that is. Okay. So if, let's say, this is my pipe and over here my fluid is flowing inside. All right, my fluid is flowing inside. So let's say over here, there is some fluid. All right. And behind this, there is another fluid element. All right. These two are different fluid elements. All right. So this fluid would definitely have some pressure, right? This fluid is definitely going to have some pressure. So what it will do, this fluid, it would try to force the fluid, this particular fluid element, this element A would force this element B to go in. All right. It would try to force the fluid to go in. All right. It would apply some force in order to allow the, in order to push this fluid element to go inside, right? To go inside. All right. And over here, again, it is going to push it and go outside. All right. It is going to push it to go outside. So in both cases, it is going to, there's going to be some force from the fluid element that is preceding the current fluid element. All right. So that force also has to be inculcated while the system is flowing. While it is still, then there is no force of the system coming from the back. But if there is, the system is flowing from the back, then in that case, there would be force coming from the back as well. So all these things has to be taken into account. All right. So on the basis of that, we come to our first law for flow processes. So let us assume that I have this as a point number 1. From here, my fluid is entering a pipe. I'll not make a full-fledged pipe. I'll just make a line as it. All right. So the fluid is going to enter my pipe over here. All right. Over here, let's say there is some heat that is added to the fluid. All right. There is some heat that is added to the fluid. This symbol is a symbol of heat exchanger. All right. If I write something like this, if I draw something like this, then this is actually a heat exchanger. All right. So this adds heat. This generally adds heat, or sometimes it also extracts heat, but generally it's adding heat. So there is heat coming in. After that, from here, it extracts some work. Some of the work, it goes out. Okay. And finally, it has come here to point number 2, from where it is going to come out. Okay. So let's say that we have the properties of the system as V1 being the velocity, capital V1 as the volume. All right. Volume of the fluid element. All right. Then P1 being the pressure of the fluid over here. In U1 is the internal energy. All right. And Z1 is the height at which it is present. Similarly, P2, V2, capital V2, U2, and Z2. All right. This is going to be here. Okay. So we are going to consider everything on a per kg basis. This has to be kept in mind. We are going to take basis as 1 kg of fluid. Okay, we are going to take basis as 1 kg of fluid. 1 kg of fluid is flowing through point 1. All right. So what we are going to do, we are going to do energy balance between point number 1 and point number 2. So in between this point and this point, whatever energy transfer has taken place, all those energy transfers have to be inculcated. All right. So over here at point number 1, we have added kinetic energy. So that is half V1 square, because it is for 1 kg basis. Therefore, we are going to take half V1 square, 1 kg. All right. M1 is 1 plus. Then over here, it will also have if let's say it has some height, then it's going to be gz1. All right, gz1 again for 1 kg, therefore nothing. Okay, then plus, now over here you also have the internal energy, so that is going to be u1. This is internal energy per kg, right? Internal energy per kg. Okay, then what we are going to do, we are going to give the work that has been given, work that has been added by this P1 and V1. All right, because as I told you, the fluid element, let's say this fluid element is going inside. So what will happen? The fluid elements that are preceding, or the fluid that is preceding this fluid element, it is going to push it. All right, it would not want to go, so it's going to push it. So that push is given by P1 into V1. All right, where V1 is the specific volume. V1 is the specific volume. Specific volume means volume per kg. So everything is per kg basis. So it's going to be meter cube per kg. So over here, I'll add P1 V1, where V1 is the specific volume. All right, this has been added plus Q. All right, all these heat, all this energy has come inside. So all these have come from point number 1. This much part has come from point number 1, and let's call this as 2. Let's call this as 3. So all the heat, it has come from point number 3. Then let's call this as point number 4. So now we are going to put this equal to the energy going out. So energy going out is from point 4 and point number 2. So from point 4, it is going to be half V2 square plus GZ2 plus U2 plus P2 V2 plus W. So this part is going out of point number 2, and this is going out of point number 4. All right. So this is your basic energy balance for a for a flowing process. All right. You have to account for all the energies that are present in the system, because of the velocity, because of its position, its height. All right, all the energies that are present. All right, then we also know that in the previous class we studied enthalpy is U plus PV. Therefore, this is going to be H1 and this is going to be H2. So this is the enthalpy again per kg of fuel. So we have half V1 square plus G Z1 plus plus H1 is equal plus Q is equal to half V2 square plus GZ2 plus H2 plus W. All right, this is the equation that we have got now. All right, this is the equation that we have got now. So let's first of all see whether all the units are satisfied or not. So V has the unit of meter per second. So V square will be having the unit meter square per second square. Okay. Then G has meter per second square and Z2 has unit meters. So it's going to be meter square per second square. Enthalpy is in joule per kg or joule per gram, right? So it's joule per kg. All right. Joule is basically Newton meter. So Newton meter per kg, and Newton is basically kg meter per second square. So this is going to be meter square per second square. So even H2, W and Q are safe. All right, all the units are balanced. All right, so now we can proceed further. So I'll again write this equation: half V1 square plus GZ1 plus H1 plus Q is equal to half V2 square plus GZ2 plus H2 plus W. All right, work input, energy input, energy out. Okay, So we'll take V1, Z1, H1, and we'll send them to RHS while we'll bring W towards the LHS. So we'll get Q minus W is equal to half V2 square minus V1 square can be written as delta V square. All right. Then Z2 minus Z1 can be written as delta Z, and H2 minus H1 can be written as delta H. So this is the basic equation for first law of thermodynamics. All right, for flow processes. This is the equation for flow processes. All right, keep this in mind. Okay, keep this in mind that this is the equation that is followed for flow processes. Q, heat added, minus work extracted is equal to half delta V square plus G delta Z plus delta H. Sign convention would be the same. Heat in is going to be positive, heat out is going to be negative. Work in is going to be positive, work in is going to be negative, and work out is going to be positive. All right. So you're going to put exactly the value along with sign over here. Otherwise, if you want, you can do this kind of a material energy balance in order to avoid any confusion. All right. So in both cases, you will have to do an energy balance, or you'll have to add or use sign conventions in order to avoid any errors in the calculations. So this was the first law for flow process. All right. So once we know this, let's try to do this problem. A system consisting of some fluid is stirred in a tank. The rate of work done on the system by the stirrer is 2.5 horsepower. Now, remember, horsepower is a unit of power. All right. So 1 horsepower. Power is the SI unit for power is joule per second, which is nothing but watt. All right, watt. All right, so 1 horsepower is 745.7 watt. All right, 745.7 watt. So that's going to be 2.5 horsepower is going to be 2.5. All right, we'll discuss that. So this is the work done on the system. All right. This is the work done on the system by the stirrer. So remember, okay, let's read the question. The heat generated due to this stirring is dissipated to the surroundings. If heat transferred to the surroundings is 3000 kilojoule per hour, determine the change in internal energy. So this is actually the same thing, right? It's just the first law. All right, so we'll simply use dq is equal to du plus dw. We have to find du. Therefore, du is equal to dq minus dw. Now, keep this in mind that our system is having work done on it. Work is done on the system, and heat is going out of the system. Heat is dissipated. Heat is transferred to the surroundings. So work done on the system is basically 2.5 horsepower into 745.7 watt. All right. And Q is equal to 3000 kilojoule per hour. All right. So this R we have to convert into seconds. So 1 hour is equal to 3600 seconds. All right. So that is going to be the heat transferred. That is 3000 by 3600. So 5 by 6 kilojoule per second, which is actually 5000 joule per second by 6 joule per second, which is 5000 by 6 watt. Got it? So that is heat transfer. So this is out, therefore this is going to be negative, and this is in, therefore this is also going to be negative. Work in is negative, heat in a heat out is negative. So over here, we are simply going to write minus 5,000 by 6 minus 2.5 into 745.7. So this is going to give us the answer in watts. All right, all the units are in watts. So we are going to get our answer in watts. So that is going to be the change in internal energy. The rate of change in internal energy is plus 2.5 into 745.7 minus 5,000 by 6. That is 1030.9 watt. All right, 1030.9 watt, or you can say 1030.9 joule per hour, joule per second. 1030.9 joule per second. So this is how the internal energy is changing. This is the change in internal energy. So this is quite simple. This does not involve flow, nothing. So it's quite simple. All right. Then we'll move on to example number 2. So this example would involve flow process. All right. So water is flowing in a straight horizontal insulated pipe of 25 mm internal diameter. There is no device present for adding or removing energy as work. The upstream velocity is 10 meters per second. The water flows in a section where the diameter is suddenly increased. What is the change in enthalpy if the downstream diameter is 50 millimeter? All right. And what is the maximum enthalpy change for a sudden enlargement in pipe? All right. So that is something that we have to understand. All right. So let's go ahead and see what they are trying to ask us in the question. So we have a pipe. We have a pipe. Through which water is flowing. Through which water is flowing. This pipe has diameter of 25 mm. Diameter of this pipe is 25 mm. All right. And it is flowing through this. The velocity is 10 meter per second. All right. The velocity is 10 meter per second. So the velocity over here is equal to 10 meter per second. All right. The water flows in a section where the diameter is suddenly increased. So suddenly the diameter is going to increase. Okay. Suddenly the diameter, it increased. Okay. Now, what is the change in enthalpy if the downstream diameter is 50 millimeters? So if the downstream diameter is 50 millimeters, this is my 50 mm. This diameter is going to be 50 mm. Then what is the change in enthalpy? So let's apply the first law. So by first law, we have 1 by 2 delta V square plus G delta Z plus delta H is equal to Q minus W. They have given everything. Q0, W0, insulated, therefore Q is 0, W is 0. Then there is nothing, no change in height, therefore delta Z is also 0. Hence, we'll simply get half delta V square plus delta H is equal to 0. All right. So now we have V, that is V1. All right. V is given. This is the initial velocity. So that is V1. All right. So now we are going to use our equation of continuity. All right. We are going to use equation of continuity. So this equation of continuity is A1 V1 is equal to A2 V2. All right. So that means pi d1 square by 4 into V1 is equal to pi d2 square by 4 into V2. All right. So pi, okay. Then we'll get d1 by d2 square into V1 is equal to V2. Now d1 is 25. Sorry, d1 is here 25 and d2 is 50. So this becomes 1 by 2 whole square into V1 is 10. which is V2. All right. So from here you get V2 is equal to 2.5 meter per second. All right. This V2 is 2.5 meter per second. Therefore, delta V square is going to be V2 square minus V1 square. All right. So that is 2.5 square minus V1, that is 10 square. All right. So that is equal to minus 93.75 meter square per second square. All right. Meter square per second square. Meter square per second square is basically joule per kg. Remember that. All right. So this is minus 93.75 joule per kg. Therefore, the change in enthalpy is going to be minus half delta V square. That is going to be 1 by 2 into 93.75, which gives us the answer as 1 by 2 in 1 by 2 into 93.75, that is 46.875 joule per kg. All right. Then they are saying, what is the maximum enthalpy change? This is the change in enthalpy. So what is the maximum enthalpy change if for a sudden enlargement? So the maximum enthalpy change would be over here. See, the velocity has reduced to 2.5. All right. Now, if they are saying that there is a sudden enlargement, all right, all of a sudden there would be an enlargement. So what is the maximum enthalpy change? So from here you get delta H. Delta H is equal to minus half delta V square. All right, that is minus 1 by 2 V2 square minus V1 square, which is 1 by 2 V1 square minus V2 square. Now in part A, they had already given that it is 50 mm diameter. But over here, they have not given. For part B, there is no diameter. No diameter specified. They are just saying that the pipe has suddenly got enlarged. All right. So if that is the case, then V2 can have any value. V1 has a fixed value of 10 meter per second as given in the question. But V2 can have any value. Right. So to maximize this entire term, we'll have to put this equal to 0. Only then this will achieve its maximum value. So this is equal to 1 by 2 into 10 square, that is 100. So this is 50 joule per kg. This is the maximum enthalpy change. So over here, the enthalpy change was 46.875 and over here it's 50 joule per kg. All right. So that was also quite easy. It was a direct formula application, right? So with this, let's move on to the last example of today's lecture. Water at 368 Kelvin. This involves a lot of things. All right. So water at 368 Kelvin is pumped from a storage tank at the rate of 25 meter cube per hour. The motor for pump supplies work at the rate of 2 horsepower. The water passes through a heat exchanger where it gives up heat at the rate of 42,000 kilojoules per minute and is delivered to a second storage tank at an elevation of 20 meters above the first tank. What is the temperature of water delivered in the second storage tank? Assume the enthalpy of water is 0 at 273 Kelvin and specific heat is constant at 4.2 kilojoule per kg Kelvin. All right. So first of all, let's draw the line diagram for this problem. So over here, I have my storage tank. This is my storage tank. Okay. So over here, water is present at 368 Kelvin. Here, my temperature T1 is 368 Kelvin. All right. It is pumped from here. Okay, it is pumped from here at a volumetric flow rate of 25 meter cube per hour. Okay, 25 meter cube per hour. So this is V1 dot, which is dot implies flow rate. All right. So if I write M1 dot, that is mass flow rate. All right. So V1 dot is going to be 25 meter cube per hour. Okay. So they have, okay, let me just write down everything that they have done. Then for pump supplies water at the rate of work at the rate of 2 horsepower. So let's say this is the pump over here. There's a pump over here. So this pump, it supplies work at the rate of 2 horsepower. All right. So work is supplied at the rate of 2 horsepower. So actually volumetric flow rate, it would be over here. I mentioned it over here. Because from the pump it is going, therefore I'll mention it here. From here, right? So this is 25 meter cube per hour. All right. Now from here, then it passes through a heat exchanger. So it is passing through a heat exchanger as well. All right. So it is passing through a heat exchanger where it gives up heat at the rate of 42,000 kilojoule per minute. So here it is giving heat at the rate of 42,000 kilojoule per minute. Okay. Then what is the temperature of the water? And is delivered to a second storage tank at an elevation of 20 meters above the first tank. So from here it is moving up, okay, and delivering water to a second storage tank, which is present here. And the temperature here is not known. Okay, and this height is basically 20 meters. This height is 20 meters. Okay. So now they are asking you that what is the temperature of the second storage tank? What is the temperature at which it is given over here? Okay. So first of all, we need to calculate the enthalpy here, H1. So H1 is nothing but M Cp delta T, right? Now, this information that they have given, that enthalpy of water is 0 at 273 Kelvin. So this is going to be used over here. So we are going to say this is actually delta H1. All right, delta H1. Enthalpy is a reference property. All right, so this actually equals to H1 minus H0, where H0 is the enthalpy at 0 degree, 273 Kelvin, and this is the H1 is the enthalpy at 368 Kelvin. All right, M Cp delta T, where delta T is going to be 368 minus 273. So this is how you'll get the enthalpy. All right. They have given us the value of Cp as 4.2 kilojoule per kg Kelvin. They have not given us mass flow rate, but they have given us volumetric flow rate. So you should keep in mind that volumetric flow rate, when we are talking about volumetric flow rate, so volumetric flow rate is basically, since we know that density is equal to mass upon volume, which is a mass flow rate upon volumetric flow rate, same. So therefore, we can multiply this volumetric flow rate by density to get the mass flow rate, right? We can multiply this volumetric flow rate by density to get the mass flow rate. So density of water is 1000, all right, 1000 kg per meter cube. So mass flow rate is going to be 25,000 kg per hour, all right, kg per hour. Then over here they have given this in horsepower, this they have given kilojoules per minute. So actually let's convert everything into seconds, all right, so that we don't have any issues. We'll get everything in watts, all right. So this is 25,000 kg per hour into 1 hour upon 3600 seconds. Okay, so this is going to give us everything in second. Okay, this is going to give us everything in kg per second. So that is 6.94 kg per second. All right, that is the mass flow. Then H0 is 0. All right, so H1 is going to be 6.94 into Cp, that is kilojoule, 4.2 kilojoule per kg Kelvin, into 368 minus 273. Let's balance the unit as well. So it is kg per second mass flow rate into 4.2 kilojoule per kg Kelvin into Kelvin. So Kelvin, Kelvin, kg, kg. It becomes kilojoule per second, which is kilowatt. Right, which is kilowatt. So we'll get this as 6.94 into 4.2 into 368 minus 270. So this is going to be 2770.833. All right, kilowatt. This is the enthalpy. All right, this is the enthalpy. All right, this is enthalpy. Okay, then next thing we need to convert this work. So work is 2 horsepower. So 1 horsepower, as we saw in the previous question, is 745.7 watt, which is 0.7457 kilowatt. All right. So 2 into 0.7457 will give you 1.4914 kilowatt. Okay, 1.4914 kilowatt. That is 2 horsepower. And then heat also we'll convert into kilojoule per second, which is kilowatt. So 1 minute is 60 seconds. All right. So minute. So that is 700 kilowatt. Okay, 700 kilowatt. Okay, so that all we have. Heat we have in kilowatts, we have work in kilowatts, we have enthalpy in kilowatts. H1 we have in kilowatts. Then one more thing is left, this potential energy. All right, potential energy. So G into delta Z. G into delta Z. Delta Z is basically this height minus this height. So since this height, it is rising up. So Z2 is greater than Z1. Right, Z2 is greater than Z1. Therefore, G delta Z is going to have a positive value. All right, this is going to have a positive value. Sign convention has to be followed. Keep that in mind. All right, so G is 9.81 and this is 20. So 9.81 into 20 is going to give us the value of G delta Z. So that is 196.2. Unit is meter square per second square, right? Meter square per second square. Since we also have the mass flow rate, so we can multiply this by the mass flow rate. All right. So when we multiply this by 6.94, that is going to give us 1361.628 kg meter square per second cube. All right, so I'll write this in the next page. So we have m g delta z is equal to 1361.628 kg meter square per second. Kg meter square per second cube. Now we know that kg meter per second square is Newton. So this can be written as 1361.628 kg meter per second square, that is Newton. All right, remaining is meter per second. So this will give you Newton meter per second, and Newton meter is nothing but joules. So joule per second. All right, so this becomes, and this can be converted into kilojoules. So 1.361, right? 63 kilojoule per second. All right, which is kilowatt. So 1.36163 kilowatt. But this is going to be positive. This has to be positive. All right, this is not going to change its sign. All right, so finally we are going to apply the law, the first law of thermodynamics. So we are going to say half delta V square plus G delta Z. All right, we'll actually multiply mass to everything. All right, so mass, because now it's not on per kg basis. So m delta v square plus mg delta z plus m into specific enthalpy. So actually plus delta H. All right. So over here, this enthalpy we have taken directly in kilojoule per second. So it doesn't really matter. All right. We have multiplied the mass already. And over here as well, Q minus W, we have multiplied the masses everywhere. So we'll delta V square is going to be 0 because there has been no information given about change in velocity, right? Mg delta Z is positive, so 1.36163 kilowatt plus delta H, we'll come to this later. Q is going out, so it is going to be negative, so minus 700. And work is supplied inside, so it's again going to be negative. So it's going to be 1.4914. 1.4914. Oh, sorry, minus 1.49. All right, so it's supplied in, so again it's going to be negative. All right. So from here you get delta H. Delta H is equal to minus 700 plus 1.4914 minus 1.36163. All right, this is what we'll get. So this is equal to minus 699.87023 kilowatt. Okay. Over here we have H1, and this delta H is basically the enthalpy here, which is H2. So delta H is actually H2 minus H1, right? The enthalpy difference. So H2 we don't know, H1 we know, and that is equal to minus 699.870. Minus 699.87023 kilowatt. So from here you get H2 is equal to H1. H1 is 2770.833. 2770.833 minus 699.87023. All right. So 2770.833 minus 699.87023. So that is going to be equal to 2270.96277 kilowatt. All right, that is H2. Now they have asked you the temperature, right? They have asked you the temperature. So what we are going to do, we are going to keep this H2 minus H0 is equal to MCP T2 minus T0. So T0 is 273 Kelvin, H0 is 0. So you'll get 2070.96277 by M is 6.94. 6.94 and CP is 4.27, 4.2. So into 4.2. Let's balance the units. But before that, this T0 will be added. So plus 273. This gives you T2. Let's balance the units over here. So 2070.96277 is kilowatt, which is also kilojoule per second. All right, 6.94 is in kg per second, and 4.2 is kilojoule per kg Kelvin. So kg, kilojoule, kilojoule, second. So this Kelvin is left, which will go into the numerator. So you'll get Kelvin. All right, that is the unit. Okay, so we'll have to solve this and get the results. So 2070.96277 by 6.94 into 4.2 plus 273. This gives us the temperature T2 as 344.05 Kelvin. Okay, this is how you solve a problem like this. So hope you people could understand the concepts behind the first law for flow process. All right, we need to find the all the scopes for energy balance, right? All possible scopes for energy balance. So we found out H1 over here. We found out W. We got Q. We got the change in potential energy. And finally, on the basis of that, we calculated H2. All right, so this is how we used energy balance. The volumetric flow rate we used to calculate the mass flow rate in this problem. All right, so this problem we specifically used mass flow rate in order to balance the units. All right, since this was in kilowatts, heat was in kilowatts, so we calculated enthalpy and potential energy. Both of them we calculated in kilowatt. So that we did using the mass flow rate. Okay, so therefore we slightly modified the first law in flow processes. So instead of taking it on a per kg basis, we took the law as this. So if it is not taken as a per kg basis, then we take half m delta v square plus mg delta z plus delta h. Over here, this delta h is not per kg. This is the total delta h is equal to q minus w. Same thing. Q and w are not per kg. They are total. They are total heat, heat and work. All right. So this is what you got. So over here, if you would have seen, I focused a lot on my units. All right. For example, here, while I calculated enthalpy, internal, work done, heat, even potential energy, when I did all these things, I focused a lot on my units. So whenever we are doing such a big and complicated problem, especially when we are involving energy balance, in that case, there is a big scope that you might do some error with the units. All right. So make sure that whenever you are solving a problem like this, so each term that you are evaluating, you should evaluate the term's value and its unit separately. All right. Evaluate the value and the unit separately. So in that case, the chances of error would be minimized. All right. So make sure we are you clear with unit conversions, unit balancing in first law of thermodynamics.